Hi, my name is Ben, and welcome to my TED Talk. Pneumonia, strep throat, gonorrhea, and meningitis are just a few of the bacterial infections that affect thousands of people worldwide every day. These bacteria enter our bodies through our mouths, eyes, ears, nose, and genital openings. Once in the body, they wreak havoc, destroying cells all over the place. And in today's TED Ed, I'll be specifically focusing on pneumonia, how it affects the body, and maybe some antibiotics to help cure it. Breathing is something that comes second nature to us humans. We do it every day, all day, without thinking about it, where in reality is one of the most important mechanics to human survival. Most people don't actually understand how much occurs during each and every breath. In a healthy person, we breathe in our oxygen through our mouth and nose, into our lungs, where the oxygen is transferred into the alveoli, which are tiny paper-thin sacs. And then the oxygen is absorbed by the blood goes back to the heart, and is pumped throughout the body. And the deoxygenated blood makes it back through the body, back into the heart, where it is pumped to the lungs, and then the excess CO2 is excreted through our mouth and nose. When the body is fighting off bacteria in the lungs, the infection that's taking place is counteracted by a buildup of a pus-like fluid called neutrophils. These neutrophils make it harder for alveoli to absorb the O2 that is being brought in. Suddenly, each breath is made impossible, conscious, and labored, and it is almost impossible to breathe. People facing this buildup usually have a hard time breathing, coughing fits, and sometimes they hear a sloshing sound in their lungs. However bad this buildup of pus may seem, it's actually trying to help the lungs, not damage them. By filling themselves with this pus filled up white blood cells, they are trying to flush out any of the invading bacteria. A major side effect of this is that for extended periods of time, or if the buildup becomes too immense, it could damage one's own lungs. With all that out of the way, it brings me to my next point, the solution to this once deadly problem of pneumonia, the first antibiotic ever invented, penicillin. Over the last 100 years, antibiotics have come a long way, but penicillin was called the first cure-all drug. Penicillin, being the origin of all antibiotics, was discovered by Howard Forley in the late 1920s, but was perfected later on in the year 1941 by Albert Alexander, who truly discovered what penicillin really was. He discovered that it was a bacterium, just one that works in cohesion with the body, instead of against it. It works by attacking the cell walls of invasive bacteria, breaking down the enzymes of the cell wall, which protect the bacteria's cell, weakening it, which allows the body to eradicate the bacteria much easier. The enzyme in the bacteria that is synthesized is called peptidoglycan, a molecule in the cell that provides the wall with the strength it needs to survive in the human body. So, for example, in the Second World War, penicillin helped drop the percent rate of pneumonia from 18 to 1%, purely by just breaking down peptidoglycan. Sadly, penicillin also has many side effects, such as causing rashing, itching, swelling, and anaphylactic shock. Penicillin has evolved into a very broad category, with hundreds of different types and variations of penicillin. In this case, we will be talking about the most versatile and common penicillin, benzyl penicillin, or by its IU-PAC name, 3,3-dimethyl-7-oxo-6,4-thia-1-azebicycloheptane 2-carboxylic acid. Other names in the industry are penicillin G, penicillin G sodium, penicillin G potassium, and penicillin V. There are hundreds of specific penicillins for a variety of different illnesses, each broken down into slightly different functional groups. These functional groups are what specializes each penicillin to perform under different circumstances. So in penicillin, there are two amide groups, a carboxylate ion and a benzene ion, and a thioether, such as shown in my image here. Starting with the benzene, it's a highly reactive molecule with a relatively high boiling and melting point, and it is insoluble except for inorganic solvents. It's colorless and has a fragrant aroma odor. The two amine groups have a fairly high melting and boiling point because of their ability to hydrogen bond, and because of the double bonds that they form, they are quite reactive. The last two groups, thioethers and carboxylate ions, haven't yet been introduced in class, but thioethers are slightly reactive, although less than thiols, and have a strong odor and an average melting and boiling point, while carboxylate ions are acidic, which helps break down in cells of bacteria, and they are fairly reactive with high melting and low boiling points. Keeping all that in mind, penicillin isn't something that we produce naturally. Although it has been discovered that our bodies create some different antibiotics, penicillin isn't something that we naturally curate. There's actually a surprisingly large amount of people that are allergic to penicillin and have a negative reaction to it. Penicillin doesn't actually do anything to prevent viruses or bacteria within the body, it's simply just a helping hand. Such as, in a sport like volleyball, penicillin is the setter. It doesn't actually score any points, but it makes sure that it helps its teammates along the way. It makes sure that it has the best effect that it possibly can, just as it breaks down the cell walls so that the white blood cells of the human body are able to do the best job that they can and defend their own body. Finally, getting into the juicy part, how penicillin actually works in cohesion with the body. Penicillin, or benzopenicillin, cannot start it orally. It's too weak to sustain the pH of the stomach, so let's just say it needs to be taken elsewhere. This branch of penicillin is especially good at destroying the cell walls of the bacteria in the lungs, hence why I chose to talk about how this type of penicillin works with illnesses such as pneumonia. The penicillin G enters the bloodstream via intravenous or absorbed through the glands of the anus and then into the blood, then travels towards the infected area, in this case the lungs, where the body is already trying to kill the invading bacteria. The cell walls of these invading bacteria are made of peptidoglycan and are very hard for the body to break down. So, the acidic polar molecules of the penicillin are able to bind to the cell walls of the invading pneumonia, which are the attacking bacteria, and break them down, allowing the neutrophils and an acidic substance released in the body and the lungs, which I talked about earlier, are able to kill the bacteria and be much more effective. This process of breaking down the cell walls continues until the majority, if not all, of the bacterial cell walls have been broken down and become susceptible to neutrophils. This usually continues for around 8 hours before the penicillin becomes useless and is excreted in the body's bile. It doesn't need to be processed anywhere before it becomes active, usually traveling directly to the site. That brings us to a close on today's TED-Ed on pneumonia, penicillin, and its chemical structures and effects on the body. I'll be looking forward to seeing you guys next week for another exciting episode. Have a good night.